Welcome back to our heat transfer class, where we are delving deeper into the fascinating world of thermal energy exchange. This video was made with the support of Energy. Remember that the introduction to heat transfer is divided into several lessons. In the fourth lesson, you can find a description of the physical phenomena that allow thermal energy to be transferred when there is a difference of temperatures. That is, the heat transfer mechanisms, which are conduction, convection, and radiation. In this seventh lesson, we're about to discover the secrets of how fast heat is transferred when temperature differences between a solid surface and a fluid come into play. Therefore, we are going to study the rate equation for the mechanism of convection.
In free convection, fluid motion is due to buoyancy forces within the fluid. Buoyancy is due to the combined presence of a fluid density gradient and the gravitational force that is proportional to density. The density of gases and liquids depends on temperature, generally decreasing with increasing temperature. Thus, in free convection there is no external force that drives its movement other than gravity. It is easy to understand that the heat transfer rate is higher when the difference in the temperature between the pot and the liquid is higher. In this way, convective currents allow heating a room or heating water in a vessel. This phenomenon is responsible for convective currents in nature and for thermal winds. At an industrial level, we can model this phenomenon with a simulator like ANSYS Fluent. This figure represents, in 2 dimensions, the cross-section of a hot pipe surrounded by colder air. In the steady state, the color map shows us how the hot air rises above the pipe. This figure is a simulation with ANSYS Fluent of a vertical wall. The air in contact with the wall is heated, its temperature increases, its density decreases, and buoyancy forces drive the hot air up. Free convection is responsible of the losses by convection in the external surface of buildings and equipment when the surrounding air is in calm. Therefore, free convection must be taken into account for calculating heat losses. In industrial applications, the circulation of the fluid is carried out by pumps, compressors, blowers or fans. For instance, a fan can improve an electronic chip cooling by increasing the air velocity on the heatsink surfaces. Forced convection is a very complex mechanism since it combines kinetic molecular diffusion or conduction within the fluid, with the transfer of energy due to the mixing of the fluid layers at different temperatures or advection. In this figure, you can see a simulation made with ANSYS Fluent. It represents the wall of a circular duct that is hotter than the fluid circulating inside it. You can see in the color map how the fluid closest to the wall is hotter than the one in the center of the duct. Moreover, you can see how this disturbed area increases its thickness along the pipe. Fluid velocities are represented in this new figure, showing lower velocities for the fluid close to the pipe wall. Despite the complexity of the physical phenomenon, the equation of the heat transfer rate for convection is very simple. In the surface of a solid at temperature Ts, in contact with a fluid at uniform temperature, T infinity, different from Ts, Newton's law of cooling states that the heat flux is proportional to the temperature difference between the surface of the solid and the temperature of the fluid in the undisturbed zone. As in conduction, the heat flux is a vector, but in convection, it is a vector normal to the surface of the solid. H is the surface coefficient of heat transfer by convection or convection coefficient. There is a controversy over who postulated the law in this way. In any case, Newton was the first scientific in performing experiments about the cooling of materials. The main problem with Newton's law is not the mathematical resolution, but the calculation of the convection coefficient, which is not constant as some scientists believed in the 19th century. What does the convection coefficient depend on? The convection coefficient depends on the fluid flow regime. That is, if there is turbulence or not. If convection is free, forced or mixed. Whether the fluid is inside a duct or outside a plate or a pipe. Also on the solid geometry. And finally, if the fluid changes phase, such as boiling and condensation, or remains in the same phase as a liquid or gas. You can see in this table typical values of the convection coefficient according to the type of flow and type of fluid. It is observed that the convection coefficient is higher when there is a phase change, as in boiling and condensation. Without phase change, the coefficient is higher for forced convection than for free convection. This is a clue to the dependence of heat flux on the velocity of the fluid at the surface of a solid. For both forced and free convection, H is greater for water than for air. This is a clue to the dependence of heat flux on the physical properties of the fluid. As you can see, the smallest convection coefficient corresponds to air in free convection.